What's going on? How's everybody doing tonight? Or, this morning or this afternoon? Whatever time period you guys are in. Hi, Psyche. Hey, Soap Opera. Did they cut your heat off? No, I like to wear, like coats and sweaters inside. I'm wearing a hat because, obviously, given the pandemic, I have been able to get a haircut, so it's a little too... Oh, I need to change the title. I always forget to do this. Fundamental. Nice. There we go. Updated. It's 4 a.m. This better be good. Well, I hope it's good. I think it's interesting, at least. Let me cut the music here. We've got a lot to talk about, really. There's quite a few things I want to talk about. The first is, as it says down here, are the fundamental laws of physics... Okay, Nashi, thank you. Are the fundamental laws of physics lies? Now, this might strike you... it's... To begin, this comes from Nancy Cartwright, very famous philosopher, very influential in the field of philosophy of science. And obviously, when she wrote her paper and book and said that the fundamental laws of physics are lies, which is the term that she uses, it's clearly meant to be provocative and catch your eye. But I think... this isn't to downplay the significance of the thesis, because it is very significant. However, it's not at all it's not anti-science. But when you're within the philosophy of science, everyone is basically on board with science being a good thing in the world. So people are fine to throw around words like, oh, science lies, science isn't real. But no one, as far as I know, mostly rejects the usefulness of science. So I feel like we should just get right out of the way this idea, this anti-scientific idea, because that's not at all what this thesis and this discussion is about. Science is a great thing. It has its limits, of course, and it should be monitored so as not to become unethical, right? But, this isn't some fundamental evangelical Christian talking point. This is coming from someone well-trained in science, Nancy Cartwright, and very well-trained in the philosophy of science. So, it's not a meme. It is not a meme. It is literal. The thesis is that the fundamental laws of physics are false, but the ramifications of this aren't perhaps as dire as you might think. But that's not to downplay the significance of the thesis, because it would lead to a complete change of worldview when it comes to science. So I think that we have to keep that in mind. But I want everyone to keep an open mind here and not come into this. That's one of the first things with philosophy. You have to come in with a very open mind. You have to be willing to change your mind. You have to be willing to adapt your worldview as you discover new arguments and new ideas, and not be, so steadfast. Yeah, lies means false. It's as extreme as lies can be, I guess. And it also has a bit more of a pragmatic force to it, because it is also accusing physicists of actually lying about what their laws mean. Nancy Cartwright here is claiming that physicists and some of the most famous scientists of all time are aware of these troubles, but sort of ignore it and lie to the public in a way. So there you go. Yeah, so there is that intentional component, Captain. There is that. And we'll go into this. I'm going to give you the whole argument. I'm going to give you the whole rundown for it. And then I'm going to propose to you some responses you could make to Cartwright and, explore some of that. Afterwards, I want to go through this article that Liam Bright, a philosopher on Twitter, posted that I saw by someone who's an anti-postmodernist, which I thought it's a hilarious article. And I think it'd be funny to just go through it and sort of pick out all of the false points that are made in the article and elucidate on what a proper theory of truth needs to and ought to look like at the end of the day. So those are the two things on... No, this isn't scientific anti-real. It's scientific anti-realism of a certain type. It is a scientific anti-realist worldview insofar as it takes the fundamental laws to be false. But what Cartwright doesn't argue is that all scientific statements are false. Interestingly, Nancy Cartwright is a philosopher of science who holds that the fundamental laws of science, so these are things like the universal law of gravitation, or Coulombs Law, or the laws that govern electrodynamics and the laws that govern quantum mechanics. She holds that all of these laws are false, but holds that the theoretical entities, or at least a subset of the theoretical entities that scientists engage with, like electrons and protons and neutrons, and certain types of, theoretical particles that are quarks, I think, are actually existing entities. Usually scientific anti-realists are of the different bent and come at it the opposite way, where they'll say that, well, yes, we'll say that the fundamental laws of physics are true, but we're not going to ascribe ontological existence. That is to say, we're not going to say that the theoretical entities that science deals with are actual existing things in the world. Hey, RJ. So, yeah, hopefully that's a good layout for what we're going to do. And if you have questions at any time, let me know. And, so let's let's dive into it. The argument essentially starts with looking at some of the fundamental laws of physics. And so if I can, I'll pull up just we can literally just go on Wikipedia and look at what the common layperson or even professional physicists view as what these laws actually say. So one such law is going to be Newton's law of universal gravitation. If I pull this up here, and I now do my look at this. You ready for this fancy shift? Oh wait. Oh yeah, here we go. Ready? Oh no, it's broken. Oh well. It's supposed to be a smoother transition than that, but that's okay. That works, I guess. If we zoom in here, zoom in really, really close. Here we go. Newton's law of universal gravitation is usually stated that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So we can see here, the force of gravity equals the gravitational constant multiplied by the product of the two masses of the two particles or objects divided by the square of the distance between the center of masses of the two particles. Okay? Now, let's just take a look. Let's take a look at this. And actually, if we go to the actual, let's go to the modern form. Every point mass attracts every other point. Okay, so this is actually, yeah, this is right. This will work. Hey, thanks so much, Cold Ass Honky, for the $10 donation. I've just started, so my Texas speech is a heavy Quebecois accent, okay? So I'll just read it back. I've just started Mackey's Inventing Right and Wrong while I read the Tractatus. How do you feel about Mackey overall? I'm not a fan of Mackey, and I don't think that Mackey's argument in Inventing Right and Wrong actually is successful. But that's not to say, like, I'm more convinced of error theory. Oh, you didn't hear it. That's right. Okay, well, hold on. It's because I have the desktop audio off. I'll replay it here so that you can all hear the Texas speech. Here we go.
Quatrième just started Mackey Inventing Right and Wrong while he read Tractatus. How do you feel about Mackie overall?
So there you go. Um, there's the Texas speech. I'm not personally convinced by error theory, obviously, but error theory has a lot more going for it than something like non-cognitivism. I don't think Mackey's argument about queer facts and everything need to be a scientific fact just to me doesn't seem intuitively correct, and I don't think that it plays out well, like especially in regards to things like mathematics or things involving abstract objects or abstract characters. I think those run into certain counterexamples that go counter to Mackey's claims, but there are more developed and more sustainable theories of moral error theory that I'm familiar with. So I think ultimately still you can make an argument for it, perhaps. Can you give an answer why you are wearing a coat inside? Because I like wearing a coat inside. I think the companion's guilt argument is a strong contender against error theory. That's also true. I'm obviously a big fan of the companion's guilt argument. And yeah, I also agree that is a pretty good that's a pretty good argument. I'm not sure, but I get the question on the stream title. It's known that we don't have a grant. No, that's not totally related to this. What were we talking about? Oh, we're talking about Mackey. Okay, so going back to this, if we examine this modern conception of the universal law of gravitation and the current form that it takes in the literature, strictly speaking, according to Cartwright, it's false, because this is a universal generalization, and that's a really fancy logical term that means it's a logical statement that applies to absolutely everything in the material universe, right? It says every point mass. So that means that at every single material point in the universe, this law should hold. And what Cartwright wants to point out is that there are instances where this just isn't true. So if you take a really, really, really small particle, like an electron, for example, this is no longer the case. The force that is exhibited by two subatomic particles is not going to be equal to the product of the two masses divided by the square of the distances between them multiplied by the constant, right? Instead, Coulombs Law comes into effect, and we can pull up Coulombs Law very simply. Coulombs Law. If we pull up Coulombs Law, it says, the amount of force between two stationary electrically charged particles is, where is it? Why would it not just have its very, does it not say, oh, the law is, yes. Okay, I can't really easily, the force of the interaction between the charges is attractive, blah, blah. Anyways, when you're talking about really small particles that are electrically charged, like electrons are, the force that is exhibited between these two particles is no longer this, but instead it's closer to this. It's closer to a force exhibited by applying Coulomb's law. So here we have a case where one of the fundamental laws of physics, the universal law of gravitation, is not true. And same with Coulomb's law, which is also supposed to be a universal law of physics, doesn't apply equally when we're talking about massive, massive, massive bodies. And so look what Stoyantic has said here. I thought gravity still applied, but the effect was very small compared to electrostatic. And that is exactly right. And that should be exactly what catches your eye here. And this is what Cartwright spends the majority of time talking about, is this idea of the composition of forces. Very simply put, Cartwright outright rejects this notion that there are component forces. Cartwright wants to say that all that exists is a resultant force. The idea that there's this gravitational force and this electrostatic force and they are both applied equally, and they are two existing things happening on the same object, creating two different forces that are then added using vector addition, she wants to say that's a total fiction. That's an illusion. All that actually exists in reality is that resultant force. So this is wrong, ultimately. We can't say that this law is true because all that exists in the world, as a matter of fact, are resultant forces, right? So when I lift my cup, okay, and I move it up and down, we want to say intuitively that there are multiple forces acting on this cup, right? We have the force of gravity pulling downward. We have the force of my hand actually physically lifting up. We have small electrostatic forces happening on a molecular level. But what Cartwright wants to say is really there's just a single force ever happening on the single cup at a given time, right? And so she draws an analogy to this idea where, like, let's say that this is directly north. When I do this, this is directly north. And when I do this, this is directly east. So say I go northeast. Cartwright wants to say, well, it's not that I'm applying it with a force towards the north and a force towards the east. There's just a single force being applied, and that is towards the northeast. We can't divide it up into a north force and an east force. That's just a handy illusion that we use. Instead, there's a single force being applied, which is towards the northeast. So the thing that I have read into based on what Cartwright wants to argue is that essentially we should abandon this idea of component forces existing and just acknowledge that there's only ever one force happening at a given time on a given object. Now, let's take stock so far of what Cartwright is saying. The first thing to notice is that, strictly speaking, Cartwright is correct. A lot of the fundamental forces that exist in fundamental laws that exist in physics today, Newton's first and second and third law, for example, are strictly speaking false. They don't apply to every single thing in the universe at all times. And in fact, as Cartwright points out, the cases where they do apply and apply, as the only force acting on an object are actually really uninteresting cases that we really don't care about. What physicists are actively studying are going to be these really complex systems involving a bunch of objects that are interacting with each other, not governed by just one force, but governed by a ton of other forces. So if physicists want to pretend like what they're investigating on a day-to-day basis is governed by the fundamental laws of physics, strictly speaking, they're lying to you. Because attached to each of these laws are going to be what are called Ceteris, I can't say the Latin for it. I think Ceteris paribus? Ceteris paribus. Ceteris paribus, that's what it is. Which is essentially a qualification amendment to any law that I have. So when I say, for example, that the universal law of gravitation applies to all objects, really there has to be a qualification to this that says in all cases where there is no electrostatic force being applied to the object, where the object is a certain mass where electromagnetic forces just don't really play a part, then you would state the universal law of gravitation. But if that's what the fundamental laws of physics are going to be, that's incredibly uninteresting, because now we've restricted it to a subset of all objects in the world, and they simply don't apply universally. So the universal law of gravitation isn't universal. It only applies to a subset of objects where there are no other forces being applied to the objects. But are laws necessarily making ontological claims? Can a law not just be a description applying in practice, but not something absolutely true? Under most conceptions of laws, I would probably say no, because laws are used primarily as an explanatory tool when we are interacting and observing different phenomena in the world. So when I drop my cup of water and it spills, I explain that with reference to the laws of physics. And as such, we want to say that the law is actually occur, unless of course you are like a hardcore instrumentalist, right? But again, like almost John, I will be putting these on my YouTube channel for sure. As with almost everything in the philosophy of science, almost everything is being done under the assumption that truth is something that is inherently built in with correspondence. So something is true, a law is true, if and only if it matches the facts in the world. And actually later on in this stream, we'll discuss some other alternative theories of truth that aren't necessarily tied to this correspondence between the laws, for example, and, actual existing states of affairs out there in the world. Because you can definitely take a more instrumentalist or pragmatic take towards truth. And I absolutely agree with that, dark and full of terrors. But if we assume that the correspondence theory is true, then it seems that Cartwright is actually definitely onto something here, where the laws of physics, as strictly stated, are either false because they don't apply universally. The universal law of gravitation doesn't apply in cases where particles are really, really small and have electrostatic charges attached to them, or they have Ceteris Paribus qualifications attached to them to the point where they are just no longer interesting and don't really play any real role in the types of complex systems that physicists are going to be interacting with. So let's take a look at this. Let's delve in a bit deep here. Like, as I mentioned, I think strictly speaking, Cartwright is wrong, okay? Because a lot, like for example, if we look at this modern formulation and even Newton's original formulation of the universal law of gravitation, it says every point mass attracts every single other point mass by a force acting along the line intersecting both points. What is crucial to this, and this comes down to how you interpret the law itself, what is crucial is that it only says that there exists a force, a single force. It doesn't say anything about the resultant force, and the resultant force, if you're not familiar with physics, is the total forces all added together. So like I was saying with the cup, the resultant force, like as I drop it, is going to be equal to the force of gravity times how like fast I drop it, right? You add all these forces together and you get the resultant force. Okay, so if I, like, let me pull up paint here. Okay, if I have an object here, right? Like, let's say it's my cup, okay? It always has attached to it the gravitational force. We'll just call this force 1, which is going to be equal to the mass times negative 9.8, which is acceleration due to Earth's gravity. And then we'll have another force, let's say force number 2 of me pulling up the cup, which is going to be equal to the mass of the cup times, how fast I am accelerating the cup, okay? So the total force is going to be equal to F1 plus F2. Does this take you guys back to high school physics or what? That's right, a free body diagram. Oh yeah, it's really taking me back to grade 10 physics. Just do 10. Yeah. Anyways, so this is going to be the resultant force right here. This is the resultant force. Resultant force. And then these ones right here are going to be the component forces. And you'll notice that Cartwright really likes resultant forces. Like, Cartwright loves resulting forces, okay? But other people don't love resultant forces. So, for example, John Stuart Mill, philosopher from, I think, the 18th century, came up with the whole theory of names. Also very famous for utilitarianism. Not the founder of it, but most famously wrote on utilitarianism. Had a view that was very different than Cartwright's, where we will say that the component forces actually exist in the world. And it's not just that there's a resultant force that exists. So this is the question we need to ask. And this is what I think it comes down to. And you might disagree with me, but I think the correctness of Cartwright's view is going to come down to whether we want to prioritize component forces as existing in the world, or whether we want to prioritize the resultant force existing in the world. So we'll call this will be the Cartwright. This is Cartwright's view. Cartwright. And then this will be Mill, okay? Mill really likes component forces, and Cartwright really likes resultant force. So what do we want to say? Do we want to say component forces exist, or do we want to say that only the resultant force exists? Well, this is the counterexample. I'm inclined to believe the Millian view that component forces exist, contrary to Cartwright, mostly because Cartwright doesn't give an argument in the paper that I read, or in the book, as far as I'm aware. There's no argument given to not allow for the existence of component forces. She references some book, I think by Anscombe, but there's no page numbers attached, and it just seems like a lazy cop-out. If anyone knows if Cartwright has ever actually elaborated on why we should hate component forces, let me know. But, let me know. And this is why I want to say so. So let's imagine a scenario where we'll have my cup again, right? And we'll have the force of gravity. And let's say that the mass is 1 kilogram. So mass equals F equals ma. Let's say that the mass is 1, and we'll say 10, like you said. Because it's downwards, we'll fly this as a force of negative 10 newtons downward, okay? And then we'll have the other force, the force of me pulling up. I'll say that I actually pull up, with the exact same force. So 1 times 10. So we'll get 10 newtons. So the total force is going to be 10 minus 10 equals 0. So there's no force. The resultant force is nothing. So it's stationary. This is a stationary body. Now, let me ask you this. Right now. Stephen Wolfram is a total hack, FYI, TKD boy. I'm just saying. Let me ask you this. When I show you that this cup is like this, we'll talk about Stephen Wolfram near the end of the stream if you want, but he's a hack. And he needs to read Philosophy of Science. And if he really has these grand discoveries, he should maybe go through peer review processes like actual professional journals in physics. So there you go. So if I'm holding, or even better, because just imagine like an asteroid being propelled towards Earth, and then we fire like a huge laser that like holds it back, so it's totally stationary in Earth's orbit, and it has a resulting force of 0 newtons. We want to explain this, and as I said earlier, laws are there to explain. So let's explain, Cartwright, why the asteroid isn't moving. How can Cartwright do that if the only thing that exists in her ontology are the resultant force, is the resultant force that exists in the world? How are we meant to explain this? Because surely everyone else is going to explain it by saying, oh, well, there is this huge gravitational force that exists between the center of the Earth and the center of the asteroid, but we also have this other force that's canceling out that gravitational force that is being emitted by this giant laser that we have constructed. Right? There's an explanation, but that explanation involves reference to these component forces here, which Cartwright wants to say don't exist. Cartwright wants to say that only this exists. But if the only thing that exists is the resulting force, then we can no longer appeal to these these compositional forces that add up to the total force. So that's why I think ultimately Cartwright's view of this just can't be correct, because in terms of providing an explanation, especially in the way that Cartwright's all about the way that scientists actually operate. That's ultimately why she believes in theoretical entities in the philosophy of science, is because scientists actually use electrons to produce certain effects and certain phenomena in the world. So it's very odd to me that she wants to say that resultant forces are the only thing exists, when if you look at any sort of explanation for any type of phenomena that scientists are looking at, or even everyone else is looking at, they're going to be talking about the component forces, not just the resultant force. And maybe you don't like, explain to me maybe why you don't like that view, but that's the personal view that I have. If a spring is being pulled from both ends, it is in tension. There's no net force, but it is very different than the same spring with no tension. That's a great example, Stionic. That's fantastic. Yeah, that's a great way to look at this. So if we have a spring like this, like let's say that they are, we'll say that they're both 1 meter long, okay? We'll both say that they're 1 meter long. It's been a long time since I used Hooke's law. But there's a is it this variable that is used to describe the spring constant, and ultimately one of them. So there's going to be some variable that differentiates these two springs from, okay, that's what it is. So the K, oh, right, okay. F equals negative kx, right, thank you. So we'll say that the K in this one is like 2. And this one, I'm not going to go into detail because I can't remember. But ultimately, if Cartwright or any scientist were to come along and look at these two springs, one is being pulled apart, the other is just stationary, there's no force being applied to either of them, according to Cartwright, because at the end of the day, there's only the resultant force, and there is no force being applied if it's totally stationary. But we don't want to say that. We want to explain that a certain spring has been extended because of the tension that it holds. That's a great example, Stionic. My K looks like an H. Yes, it does. So she's only saying one force can be applied. She's saying that only one force can actually exist in the world. There's only the resultant force, which is the sum of all the other forces. Cartwright describes the illusion, the facade of vector addition. So this is the way that we arrive at the resultant force, but what we're doing is just some fancy math that is really just getting us to what actually exists in the world, which is that resultant force. So there you go. So yeah, I disagree with Cartwright. I think that the Millian view is ultimately the correct one, because I'm inclined to think that these component forces do exist, because they're the only way that we can really explain the phenomena that we observe in the world. And if we just solely restrict ourselves to resultant forces, we have no way to explain things like stationary objects, where forces are, according to Mill, annihilating each other, which is a bit of a weird term. I don't know why he says annihilating. They cancel each other out. Or something like two springs that are stationary, but clearly we want to refer to something like Hooke's law that refers to the spring constant that differentiates the two springs, which where one is by default actually is a shorter length than the other, but more tension is being applied to one or the other. So does everyone understand? Does this make sense to people? Does it make sense? Does Cartwright's position make sense? And do my objections to Cartwright make sense? Kinda, sorta. If anyone has questions, feel free to ask. Fantastic. Wow, I gave an explanation because it's, some stuff makes, some stuff in philosophy is a lot simpler to understand than, for example, metapistemology. So this is a lot more conducive to a quick, 30-minute summary of something. The other thing I wanted to, we can take a look now at, someone was talking about Wolfram, right? Bruh, he's built an entire mathematically coherent online calculator and language built around this hack calculator. How is he a hack? Elon Musk also created SpaceX and created like the first piece of space equipment that can land itself. But he also thinks that Marx was a capitalist. So ultimately, just because you're good at one thing doesn't mean that you're going to be good at something else. Wolfram might be a really good mathematician. And he might be good in certain areas, but that doesn't mean that he has any sort of expertise on when it comes to questions in theoretical physics and the philosophy of science about a grand unified theory for science at the end of the day. So there you go. Like, for example, just because someone is studying black holes or or string theory doesn't mean that someone is, again, look, I think that this is one of those areas where physicists really need to talk to philosophers, because the question about a fundamental theory of physics, a grand unified theory, and remember, this is not just there's a lot of stuff that we could go into here, but a grand unified theory is supposed to explain everything, right? So nothing is off limits, according to, if you are advocating for grand unified. Everything is explained by this grand unified theory. That includes things like consciousness, every single special science that exists, like anthropology, archaeology, economics, psychology. Everything is ultimately supposed to be reduced down to this base grand unified theory. But first of all, theoretically, I don't even think that is possible. Second of all, I don't think that actually science, this might seem contrary to this, but I'm working within Cartwright's own sort of theoretical worldview with the correspondence theory of truth, but I don't actually think that science is in the habit or has the role of explaining things. I do not think that science is explanatory. I think that science is predictive and pragmatic. That's my own personal interpretation of science. I don't think that science can really explain reality at its root, but the formulation of the grand unified theory itself would need to be able to be explained by the grand unified theory. That's exactly right. You run into there have been many, many objections to the idea of a grand unified theory, but my favorite is definitely the halting problem, essentially applied to the grand unified theory. So I think ultimately, if science is supposed to explain everything, how can science explain itself without being just viciously circular? I also love the halting problem. The halting problem is very, very interesting, and I need to read more on computation and Turing machines and stuff. Could you see science as a tool trying to describe something that is graspable for people so we can move forward with our understanding and eventually as a race? Yeah, absolutely. 100%. It is a tool. It is an instrument. That's exactly what I would view science as, for sure. Oh, I don't think right off the top of my head, Silent Soul, Taker, I don't think I could explain to you the halting problem. I don't think I could do it for you right now. That's a really complex problem. There are some great YouTube videos on the question, though. But it's especially interesting as applied to mathematics, because if you look at, I'll just briefly say this a lot. If you're not familiar with the background, it won't make any sense to you. But Hilbert's program was essentially undermined by Gödel's incompleteness theorem, and Gödel's incompleteness theorem can be explained in terms of things like the halting problem, and in terms of things like Turing numbers and other stuff like that. That's the vaguest kind of explanation I can give to you without starting from square one. Yeah, Wolfram doesn't even really have a theory, as far as I can tell. Right? He's yes, it's a project for discovering the theory. That's right. He's hyper focused on cellular autonoma, right? That's still his big thing. Which is interesting, but you know. I thought the unifying theory was just meant to consolidate quantum mechanics and general relativity, or is that wrong? That would be a great step towards unifying theory for sure, but that's definitely not all that is meant by the unifying theory. There's definitely something more that is needed. So if we were to talk about reduction, scientific reduction, or reductionism, or a unified theory of science, the general conception is that, if I erase all this, the general idea is that, like, let's say we're talking about economics. I'll do economics then. So, like, we have economics, and that, all right. So we'll say that a law in economics entails another, or we'll call them laws. So, like, let's say this is an economic law, right? And this is a second economic law, and the instantiation of the first law entails the second economic law. What the grand unified theory of physics, or the reductionist program, wants to say is that for every law of a special science, like economics or soft science, however you want to call them, there should be what are called bridge laws that exist between the economic one and a physical one, or a law from physics. So for each of these, I should be able to just quickly substitute out each of the economic laws for a corresponding physical law, which basically produces another entailment clause that only uses the laws from physics. So every single law that we have that governs one of the special sciences, like a law about what is the one that Jerry Fodor uses in his paper on reduction? It's like an exchange. It's a law about monetary exchange. It's someone's name, and I can't remember because I have an awful memory. I don't know. It's something. But for every law that entails another law, you should be able to reduce every single law down to a physical law. So every law that governs neuroscience or geology or psychology or economics, etc., should all be reducible to purely physical laws that govern the entities described by physics. And obviously, it's going to be transitive, right? So with economics, it would probably go down to neuroscience, right? And then from neuroscience, it would go down to, God, I don't know. I guess biology, right? And then biology to chemistry, and then chemistry to physics. And so you basically get these one-to-one correlations between... not correlations. Sorry, it's not just correlation, because not only is there correlation, but there's a direct dependency, or explanatory dependency between physics and something like economics, or what? Reductions. Yeah, and these are called bridge laws. These right here, bridge laws. They're also very, very big in the philosophy of mind, because there are people that argue that consciousness is reducible to simply neuroscientific properties that exist in the world. So every single mind state that we have corresponds to a certain neurophysical, neurochemical, physical state, etc. So hopefully that makes sense. Where are you getting this definition of grand unified theory from? I mean, it depends how you want to define it, right? But if you're looking at the philosophy of science literature, how I'm talking about is usually how it's going to be defined. But then if you look at, these famous figures in physics, this is what they were doing. They were trying to produce something like this. So this new conception that you might have between where a unified theory of physics is simply meshing quantum mechanics with something like special relativity, ultimately solving quantum field theory, as far as I'm aware. That's not usually what is going to be meant by the grand unified theory. Nor do I really understand how Wolfram's solution would solve quantum field theory. But I'm not a physicist, right? So I'm not going to. But I follow a lot of physicists, and I follow a lot of people that study this type of thing, and you can basically hedge your bets that if you aren't willing to publish this in a peer-reviewed journal, you should stay intensely. Sean Carroll was talking about this the other day on Twitter. You should remain intensely skeptical of it. Okay, things in physics need to undergo peer review. Everything needs to undergo peer review ultimately in every discipline. And the fact that Wolfram doesn't want to do that, and instead, I guess he's streaming on Twitch. I don't know. That should bring great doubt. There's an amazing article on Wolfram that sort of documents his life about how he started out as a really great... Actually, I should bring someone on to talk. I should bring on Lichtenstein, who is a Twitter user who studies philosophy and physics, I think at the University of Oxford. I should bring him on, if he'd be up to do it, to talk about this issue, because I think that would be... same thing with Weinstein's theory as well. That's exactly right. I think that's what specifically Sean Carroll was referring to, actually. But I'd love to have Lichtenstein on so that we could discuss this topic in particular, because I think it's very interesting and very important as well, mind you.